we will move ahead to chapter 4. Gonna pick it up reading the lecture document that you've got there. Quite a bit to talk about before we get to the first practice problem. So I'll start there at the top. Chapter 4 is the discrete random variable or discrete random variables. So some of those words look familiar. Let me begin just by pointing out a couple of examples of how this might be useful to someone. It says a store owner may want to estimate the number of customers who entered the store on a Saturday. Certainly, that could be very helpful if they could get a good guess at how many customers they'll get on a Saturday. And you notice, some of the words from discrete random variables come in there, right? The number of customers would be a discrete quantitative variable. Second example, a university may want to know the dollar amount that will be donated by alumni during the coming fiscal year. Definitely they want to get a good idea of that. And even that dollar amount would be a discrete random variable. These are examples of a discrete random variable, and each have associated probabilities. Okay. So it's the fact that it's a probability is going to be involved here. That is key. And of course, that's going to tie all the things we do in chapter 4 very closely to the things that we did in chapter 3. So let's finally get the definition of a random variable. A random variable represents a numerical value with an associated probability. So what we're saying there is not all of the possible numerical values will have the same probability. And that was pretty much always the case in chapter 3, right? So, if you flip a coin or roll a die or draw a card, right, all of the outcomes have the same probability. And we're going to say, no, that's not going to be the case anymore. Different outcomes could have different probabilities. Okay, and then we can advance that definition and call it a discrete random variable. And so the discrete just adds on the fact that our numerical values are now discrete, which we might say values that are countable. But certainly we've discussed discrete versus continuous back in chapter 1. And if you are curious, I've got that note right there. We will study the continuous random variable in the next chapter, chapter 5. So it makes sense, right? We do the discrete random variable, then we do the continuous random variable. Okay. A probability distribution. So this is really nothing new. It's just a new name. A probability distribution provides the probability for each value in a graph, table, or formula. Those are things that we're doing in chapter 2. So you might think like a relative frequency histogram would be a probability distribution because it shows, we called them proportions in chapter 2, but you could call those probabilities as well. Okay. So we'll see examples of that right now, all these things. So an example, this is a baseball example, fitting for a stats class. The MLB, also known as Major League Baseball, the MLB championship is known as the World Series, if you're not familiar with baseball. Of the two teams, it's the first to win 4 games who wins the series. So the series will consist of either 4, 5, 6, or 7 total games. If you're not familiar with baseball or other professional sports, even basketball and hockey do the same thing as baseball. So their championship, it's not just one game. They call it a series. And so it's the first team to win 4 games. So it's possible that the series could only last 4 games. If the same team wins every time, then it's over. But, it could go 5 games or 6 or at most 7, because at that point someone would have had won a 4th game by the time you finish game 7. Okay. Which, in my personal opinion, that's a far better way to decide the best team than, say, like in the NFL. All right, in football, they just have one game, the Super Bowl, and maybe you have an off day, But when you have in baseball or basketball or hockey, right, they play a series, and there's little doubt that the better team is going to come out, okay, as the winner. So, getting to the example, here are the number of games played in the World Series from 1965 to 2004. How many games did the World Series last? And again, it could have been 4, 5, 6, or 7 every time. So we see that table. So that table tells us how many times the World Series went each number of games played from 1965 to 2004. So we can see how many times were there exactly 4 games played? Well, that only happened 8 times. How many times were there 5 games in the World Series? Actually, even less, only 7 times in all those years. How many times were there 6 games? And, well, there were 9, so those are all pretty similar. And then how many times were there 7 games? By far the most, 16 times that happened. And so, hey, that's good for fans. We all like a game 7. It's fun. Okay. So, all right, that's how many times each one occurred. But all of these have associated probabilities. So we look just to the right. The probabilities for each value are as follows. So we'll look at the probability that there would be 4 games played. Okay, well, how do we calculate the probability of there being 4 games, right? If it's like if we select one of those World Series at random. You're like, well, it happened 8 times. Why is it out of 40? Why 8 over 40? Well, because 1965 to 2004 is 40 years. That's 40 World Series that occurred. Or, you could also find that by adding the values in the frequency. Those add up to 40. Okay, so 8 out of 40 times, which works out to a very nice 0.2. What's the probability that there were 5 games? Well, 7 out of 40, 0.175. What's the probability of 6 games? Okay, we got the idea. 9 out of 40, 0.225. And the probability of 7 games played, 16 out of 40, which works out to a very nice 0.4. And just below that, we see the probability distribution. That is a relative frequency histogram. And you can see the numbers are kind of small. If you enlarge that document a bit, you can see the probabilities there on the left. And you can see the number of games played at the bottom, starting with 4. And so, anytime there was 4 games, we just stack all of those into that first bin. So that goes up to 0.2, and then the 5 games, the 6, the 7. And notice there we see the number 8, but that just is the boundary for that last bin, of course. And, that gives a nice, I would say that's superior to the table, because that really gives a nice visual of just how many more games there were that went, say, all 7, that went to a game 7 compared to the others. Okay. We're almost ready to do one ourselves, but I've got a couple things at the top of the second page. To represent all possible values of the random variable, we're going to use a capital letter such as capital X. To represent one particular value, we're going to use a lowercase of the same letter, like a lowercase x. So this is kind of a statistics sort of a thing and notation that you really only see in statistics. And if this seems bizarre, I completely understand, because we don't do this sort of stuff in other math courses, right? We don't sometimes use a capital X and other times use a lowercase x. And here they don't exactly mean the same thing, but they're very, very close. It's just a nuanced difference, but this is the way statisticians have been doing it for a long time. When we represent all of the possible values, we use the capital X. When we represent one particular value, we use the lowercase x. Okay, so we're going to see that in our first practice problem let's get right to it. Say capital X is the number of heads that appear after tossing 3 coins. Construct the probability distribution as a histogram with relative frequency. Okay, you may have noticed my rock here to keep my paper from blowing while we were reading that. All right, chapter 4, practice problem number 1. Okay, so we've got some work to do before we, make our histogram. So we're talking about tossing 3 coins and seeing how many heads appear on those 3 coins. Okay, well, what are the possibilities for how many heads that could appear when you toss 3 coins? And you think, okay, well, maybe one head. There could be one head that appears. Maybe there's 2 heads, right? Maybe all 3 come up heads. And you don't want to forget maybe 0. Maybe none of them have a head. So maybe we start with that. So there could be 0 heads, 1 head, 2 head, or 3 heads. And we got to go through and think about all the combinations of ways we could do each. So I'm just going to show you what I've got here, and then we'll talk through it. Try and adjust the focus a bit. Okay, that's better. So we're saying capital X is the number of heads that appear. And then the lowercase x is each individual value. So little x could equal 0, no heads. Little x could equal 1, 2, or 3. And then off to the side, you see I've represented all the ways that each one of these could occur. So if you remember from studying probability, the order matters. So when we toss the 3 coins, we need to think like there's a coin number 1, a coin number 2, and a coin number 3. So our first toss here, all 3 coins came up tails, right? We've got 0 heads. So tail, tail, tail. Coin number 1, coin number 2, coin number 3. There's only one way that can happen. When it comes to getting 1 head, there are 3 ways that could happen, right? Coin number 1 is a head and the other are tails. Or maybe it's coin number 2 that's a head and the other are tails. Or maybe it's coin number 3 that's a head and the other are tails. 3 different ways that we might get just 1 head. We go to 2 heads, and it's kind of similar to the other one. You could even think just 1 tail, right? So 1 tail, 1 tail, 1 tail. So we got head, head, tail, head, tail, head, tail, head, head. All the ways you can get 2 heads. And finally, how many ways can you get 3 heads? Well, just 1 head on the first, head on the second, head on the third. Okay. And it's good to note how many total different ways this could occur. And we see, okay, well, if we count them up, right, 1, 2, 3, 4, 5, 6, 7, there are 8 different outcomes for the number of heads that we might see. Okay. And so we'll say, all right, we're supposed to construct a relative histogram. We need probabilities. Okay. What we're looking at, these right here, the x's, this is the discrete random variable, x, right? Right, makes sense, like x represents the variable. So we notice these numbers are discrete, 0, 1, 2, 3. Okay. Those are all of the possibilities for the number of heads, but they don't have the same probabilities. As you can see from the ways over here, it's more likely that you get 1 head than getting 0 heads. And the 1 and the 2 have an equal probability, and the 0 and the 3 have an equal probability, just thinking the number of ways that these can occur. Okay, so let's actually calculate these as decimals, starting with 0. Looking at the total number and looking at how many ways you can get 0, what's the probability of getting 0 heads? We would say, all right, we kind of like to write this out in words, all right? The probability of 0 heads, well, there's one way that can happen out of 8. 1 out of 8, 0.125. Okay, how about the probability of getting 1 head? Well, there's 3 different ways that can happen out of the 8. 3 out of 8, 0.375. And okay, we get the idea. 2 heads is also 3 out of 8, and all 3 being heads is also 1 out of 8, and so we see the decimal versions there as well. Okay, so they don't have the same probabilities, right? It's 3 times more likely you get 1 head than getting 0, or, etc. All right, we're not done. We need to make this histogram, so we're using our probabilities there. And I'm just going to show you my work and talk you through it. So we needed, we create our axes, right? And at the bottom, we say, okay, we're starting with 0. So I'll mark 0, 1, 2, 3. 3 is the last one, but I also need a 4 just to be the boundary for that final box. So my random variables 0, 1, 2, 3, and then we got to have the one more to finish it. Okay. Then you might think, well, how should we scale? Well, in this case, it's actually really nice because it's all, out of 8. So 0.125, and then maybe make 0.250, and then 0.375, and we can draw our boxes. So, the 0 here is this first box, only one way, 0.125. As soon as we hit 1, right, now we've got 3 ways, so it's 3 times as tall, 0.375, and then the same for 2 ways, or 2 heads, and then the same for 3 heads, like so, and there is your answer. And again, the histogram really conveys the relationship of these, I would say, even better than the numbers. And, these aren't too complicated, but seeing that graph is very helpful. Okay, let's stop this video here. More to come.